Hello! So in this video we are doing the various ratio tests. So in the text we're using, at least at the time of this recording, the author has a fundamental ratio test, which is this one, the ratio test, which is the sort of yellowy-orange one, and Cauchy's ratio test, which is the blue one. He has them all separate theorems, proves them all separately. Really, sort of historically and mathematically, what is going on is that we have sort of the fundamental one sort of comes first and gets the underlying idea. Then you can make an improvement upon it in making the hypotheses a little easier to digest. That's the yellow one, yellowy-orange one. And then, of course, Cauchy comes along and makes it more rigorous using his ideas of limits and how to rigorously prove limits. I shouldn't say his ideas, but sort of puts it in the terms that he's been doing at that time with sequences and series, that also uses the sort of standard, at that time, rigorous notations of, of limits. So these are all sort of advancements on the one theorem that historically over time they're making it more and more accessible, easy to apply, and more sort of concretely understandable. For that reason, I'm going to prove the fundamental one, and then moving from the fundamental one, I'm going to be doing the two corollaries. Well, I'll be doing the other two theorems as corollaries, as they really are kind of follow-on pieces to this theorem, the original fundamental one. So I'm going to try to put all three on here. Almost certainly I'm going to have to do some editing magic in order to get it all to fit, in the sense that I might do one or two proofs and then have to erase those to do the last proof, but we'll see how it goes. But I want to do all these in one video instead of having sort of three really short videos where if you watch any of the corollary ones, like these things, you effectively have to go back and watch the first one anyway, because it's really just applying this one to get that one, right? So this way it's all sort of together in one spot. All right. I'm also going to try to color code this. Usually I try to make it separate so it's easy, what's the proof and what's the statement. Instead I boxed off the statements, and now I'm going to try to match the color to the proof, the color of the statement to the color of the proof. So using the pinky one here. So the original fundamental ratio test, I've just written ratio test because the other ones are corollaries. The fundamental ratio test, so this says that suppose you have some AN and BN. These things are sequences of real numbers. And in particular, these things, I think I might have forgot to write something. I think these are supposed to be real positive numbers, are they not? So let me just double check. Yeah, sorry. So AN and BN are sequences of positive real numbers. My bad. So strictly positive real numbers. And we're supposing that there's some capital N in a natural number, so that this sort of ratio of terms is always going to be less than or equal to the ratio of the other sequence's terms for n bigger than n. So what that's saying is the ratio of the next term to the previous term for the A's is going to be eventually smaller than the same relevant ratio of next term to current term for the B's. And so if you have this set up, then the theorem says, well, if BN converges, that series converges, then the series AN converges. So in some sense, it's similar to the idea that if AN is smaller than BN and BN converges, then AN converges, except instead of using the terms directly, we're now using the ratio of the terms, okay? So suppose I have all that stuff up there, and so suppose I have all this stuff. So notice, and now I'm over here, haha. So I realized after a little bit that although technically what I was writing was not wrong, at the same time it was really confusing and a bad way of doing what I wanted to do. So because I have an editor, I am going back, cut out all that stuff, although now I'm going to be teleporting around, or I did teleport around. So I'm just going to restart here at this notice and move forward. So again, notice multiplying by, so I want to do AN over BN n plus 1 on this inequality here. So the an is going to move over, the bn plus 1 is going to move that way, so I'm going to get a n plus 1 over b n plus 1 is less than or equal to a n over bn. So denote Cn to be the sequence an over bn, just for the sake of sort of niceness, right, for notational clarity. So if I think about it as an over bn, then Cn is this one. Cn plus 1 replaces both of these with an n plus 1, I get that. So in particular, this gives me Cn is a decreasing sequence. Right, because as I increase from n to n plus 1, the ratio gets smaller, and Cn represents the ratio, not just the an or the bn. So now, if we fix some, let's say n, I'm going to notice for little n bigger than capital N, because this is decreasing, I'm going to get that. So Cn is decreasing, which means the bigger, sort of earlier in the sequence, is bigger, meaning that the an over bn for capital N, which is really Cn, this is going to be bigger, or at least as big, as C little n, because n is even further and it's decreasing. And this is little n over b little n, meaning that as I pick bigger things, I have some universal bound thing, okay? So if I denote that particular fixed capital N, so I denote a capital N over b capital N by, let's say, m, then I get that for big enough n, right, the eventually bit, I'm going to have that an, I guess, sorry, I just double checked, I have used capital N, so let me make this n capital N prime. Which actually does matter because that's in the statement of the theorem, it's not in a different case. So I need to make sure that that's fine. Okay, good. So this is m. So this is telling me that for little n over bn is going to be, this thing is going to be less than or equal to capital M, i.e. an is going to be less than or equal to capital M times bn. But we know then that bn and an, they're both positive real numbers, right, for all the n's. And I have that an is bounded above sort of by this pointwise pseudo-uniform bound, right, this thing here, this m times bn. And that's exactly what the comparison test is for, right? The comparison test from before says that if, under these conditions, if bn converges, an converges, which is exactly what we want. So our result follows by the comparison test. All right. I'll make a note because I guess I forgot to technically write this, and I should have. I can write it up here. So there was one little thing, which is that, strictly speaking, I'm just saying there's a sequence of real numbers such that there's a capital N so that this holds after that big N. And I just sort of went with it right at the start. And that's, as you may have remembered from a previous video, I went through the rigorous way of how to do this for the eventually, works in the tail thing. And then I said, for most future things, I'm going to assume without loss of generality, WLOG, because the first finite terms don't matter for convergence, suppose n equals 1. Meaning that suppose that this thing happens at the very start, right? So I'm sort of throwing out however many it took to start the pattern of having this ratio work, because those finitely many don't actually affect the convergence. So I can do this without losing the generalized version of my proof. Okay, so that's the fundamental ratio test right there. That's all there is. That's all there is to it. We've already done the comparison test, which is sort of the harder one, or I should say it's the stepping stone that gives us a nice proof for this one. Okay. All right, so let's move on to the first corollary, what the book calls the ratio test as opposed to the fundamental ratio test. So color coding here. So this corollary says, okay, so I'm not even worrying about the bn's now. Suppose there's an an sequence of positive real numbers, right? So again, it's strictly positive real numbers, just like over here. And suppose there's some capital N so that this ratio is always less than or equal to alpha for some alpha that is less than 1 and is a real number, right? So alpha could be 1/2, it could be 0.999, right? But it's strictly less than 1, that's important. Then we're claiming that the series AN converges. So again, I'm going to do the same idea. So without loss of generality, suppose n equals 1. Because again, we're talking about convergence here, so we don't actually care about the first finitely many terms. As a footnote, I will mention that I had a professor in undergrad who told me something that is a very good idea to sort of be aware of as a undergrad or first, second year grad student when it comes to math proof classes, which is that most of the time when you use the phrase without loss of generality, you have lost generality. So use that statement at your own peril. That being said, I am teaching this class for a reason, so I can justify using this without loss of generality. However, there's no reason why you can't do it the rigorous way, so when you're doing this, say, in homework, exams, in your own work, feel free to actually do it the rigorous way so that you know you haven't lost any generality, okay? I'm doing it due to lack of space and trying to make this as clear as I can. Okay, so suppose I have such, an AN now. So suppose that, and suppose, so this isn't without loss of generality, this is just, so stop there, and now suppose this, then an plus 1 over an is indeed less than or equal to alpha less than 1, okay? So define Bn to be alpha to the n. Okay? Notice so I don't need to write this in the proof, but I'm going to point it out just for pedagogical reasons here, that if I took Bn plus 1 over Bn, well, that's alpha to the n plus 1 over alpha to the n, which is alpha, right? So in particular, notice then that since an plus 1 over an is less than or equal to alpha, and alpha is Bn plus 1 over Bn, then by the previous theorem, this is a corollary of, I now have a Bn that is greater than or equal, right, in that ratio, greater than or equal, for each of the n's moving forward. And that tells me then if this series, the Bn's converge, then the series AN converges. So this says then by previous theorem, if the series Bn converges, then the series An converges. Okay. But that's not quite what I want, right? This corollary definitively says definitely the series An converges. But notice, I guess I should, that's just bad writing, notice and notice, so maybe I'll say further. So furthermore, Bn is what? Well, Bn, so the series really is what I care about. Bn is a geometric series. And alpha is less than 1. So this Bn converges. So since Bn converges, An converges, and we're done. Okay. So this corollary is basically sort of the classic way a lot of these things are used, which is that I have some information on this A that just sort of is there, and it's up to me to develop a B so that, to develop a Bn so that the Bn satisfies the conditions of what I need, and yet gives me that the Bn converges so that I can get that the An converges, right? So this is sort of a classic way of going about this. In this case, again, a very common way to use it is that I pick Bn to be a very simple, very nice thing that I could tell without any effort converged. It's just a geometric series, right? So I didn't have to go through and like really hard bare knuckle show that Bn converged because I picked a Bn that I already have a theorem telling me it converges, so I can just be like, ha, there we go, done, right? I don't have to do a lot of extra work. All right, so then we're off to corollary 2, the last one here. So I'm going to point out the key difference between these because in some senses it seems like these are all very, very similar, and they are, right? Like I said at the beginning, these are all sort of improvements on a theme. But in the first two, I need to know something about every possible An plus 1 over An. Granted, after a while, right, eventually blah happens. But that can be very sort of tedious to show in a proof that, you know, for generic n, I definitely have this fact, especially if you get Ans that sort of are weird, right, where you have things like it's this if n is prime, it's this if n is even greater than 2, and it's this if n is neither of those other things. And then you're starting to be like, okay, well, I have all these different possibilities where I have this form on the top, this form on the bottom, or the other way around, or this or that, or blah, 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 right? And it gets really tedious to try to show this kind of setup for every possible n form combination craziness, right? So cue Cauchy coming along, and Cauchy designed his so that all you need to care about is the limit of the event, so that you don't really need to worry about whether or not, you know, the possible, like, this thing over that thing, different forms doing different things, as long as you can calculate the limit regardless, right, as long as that limit exists, then you can say something, right? So Cauchy is saying, okay, so again, we have an An being now a sequence of real numbers, not necessarily positive, except we also say there's some capital N so that An is non-negative for those things. So really what I'm saying is that An is a sequence that is eventually non-negative. Still not strictly positive, but eventually non-negative, right? Is that right? Hold on, sorry. I think it's actually just, yeah, I'm sorry, no. This is strictly positive. Whew. I was like, wait, that doesn't make sense. Yeah, so this is An is indeed strictly positive. There we go. Sorry about that. So he's saying, okay, an is a sequence of real numbers, maybe positive, maybe negative, maybe 0, but after a certain point, they are always strictly positive, right? So these are eventually strictly positive. So just like every time before, without loss of generality, I'm going to assume, suppose n equals 1. And again, this is just because what we're dealing with is limit stuff, so anything that I'm doing, I can take sort of a big enough number that I guarantee I'm past capital N and do other stuff. So I don't care about the finite sort of first finitely many terms. So without loss of generality, I just assume there aren't any because I'm not going to worry about them regardless. All right. So I have two different statements here. I have that this one, if, so in fact, let me maybe 1, 2, right? If this limit is less than 1, then I get something convergent. If that limit is greater than 1, well, then it diverges. So for part 1, to note the limit as n goes to infinity of an plus 1 over an by L, which again we're noting is strictly less than 1. Thus, there exists n prime so that, so the limit being less than 1, right, the limit equaling L means that I can take sort of deep enough in that sequence such that I get as close to L as I want. In particular, I'm going to get that an plus 1 over an is going to be close enough to L that I get somewhere between so that the most it can be is still less than 1. So I want no bigger than L plus, so L is less than 1, so 1 minus L over 2 is positive. So this is my epsilon. So I don't need this side, but just to make it clear that that's my epsilon, I'm doing L minus 1 minus L over 2. So if I actually compute, like if I clean this up, what this actually looks like, I would have 2L over 2, so I'd get 2L minus L, so this would be 1 plus L over 2. And the reason I picked that is because, again, I don't think this is part of the proof, but just to show what's happening, I have whatever the actual sort of ratio is, which is hitting at L, right, that's the limit, L. It is something less than 1. So if I take the sum of them and divide by 2, I'm taking the average. So that's here. This is 1 plus L over 2. So I'm doing, so this is maybe like 0 or something over here. I'm picking deep enough that an plus 1 over an is somewhere in this interval, okay? Importantly though, this thing, no matter how big it gets, is still less than 1. So I'm going to denote this, right, I'm going to do that colon equals. I'm defining this value, 1 plus L over 2, to be alpha. Thus, if I move the an over, right, I have an plus 1 less than or equal to alpha times an, because I moved the an over, right? But this, alpha, is less than 1. So this is, in particular, strictly less than an. Right? So in particular, an is a decreasing sequence. But sort of importantly, right, so what am I after? I'm after that this series, an, converges. Well, I've shown that if the ratio an over an plus 1, I guess I don't even need to show this, but it's maybe helpful. This an plus 1 over an is being less than or equal to alpha is less than 1. That's exactly what I just did, right? An plus 1 over an is less than or equal to alpha, where alpha is still less than 1. So by corollary 1, the series an converges. So I guess I don't need that line, but it's sort of showing what's happening. It's the same idea, right, that was happening over here. So this is the proof of 1. So then the proof of 2, I'm going to do same sort of idea, but it's going to be a little more work because I can't use corollary 1 here. So similar, so still n equals 1, similar to number 1, right, in the proof, there exists n prime, so that if n is greater than or equal to n prime, if I have that this limit is L again, so, or L prime, I'm going to have that the limit as n goes to infinity of an plus 1 over an, which I will define as L prime. This is greater than 1. So for n greater than or equal to n prime, I'm going to have that same ratio, an plus 1 over an. So this is, again, I'm setting up this idea that because it's a limit, I can get within epsilon close. But now I'm going to do the same thing, except now this is going to be 1, and that'll be some bigger number, I don't care. But I'm going to pick an interval around it so that no matter how far left you try to go from the limit, you're still strictly bigger than 1. That's the idea. So this thing is going to be, yeah, I don't need to. So I'm going to do the same idea here, only now I care about the lower side of the epsilon. So this thing is going to be greater than or equal to L minus the epsilon. The epsilon I'm going to choose is going to be L minus 1, which is a positive number because I know that L is bigger than 1. Sorry, L prime in these cases. L prime is bigger than 1 over 2. Which again, I will note if I clean this up, so I'm going to get 2L minus L plus 1, so that's going to be, again, 1 plus L prime over 2. Where now, I'm taking the average of L prime and 1, so in this case, if I have, do another like quick little sketch here, I have L over here, I have 1 over here, and so the average of 1 and L, I did again, L prime is going to be here. So I'm landing somewhere in this area, 1 plus L prime over 2, right? And importantly, this is still greater than 1. Okay, so that's the idea, is that I'm choosing an epsilon so that no matter how far to the left, when I subtract epsilon, no matter how far to the left, I'm still going to have something strictly larger than 1. So this tells me, again, if I take this thing, right, so for n greater than or equal to n prime, I'm going to have that an plus 1 is greater than or equal to 1 plus L prime over 2 times an, right? That's moving the an over. But as mentioned, this is bigger than 1. So if I get rid of it, I'm going to make it only smaller, right? Because I'm multiplying by a number bigger than 1. This is bigger than an. So in particular, an plus 1 is bigger than an, i.e. an, the sequence, is, so actually this is strictly larger, sorry. Yeah, this is strictly larger, which is actually kind of important. It's not necessary, but it's relatively important. So an, the sequence, is strictly positive. I guess I can write just positive. I don't need it to be strictly. I'm sorry, I said positive. What I meant was increasing. We already knew it was positive, and in fact, strictly positive. Right, because I'm assuming at n equals 1 that I have this an is strictly positive. But since an is greater than 0, this means the limit as n approaches infinity of an, well, I have that it starts strictly greater than 0, and then I have that it's increasing. This is certainly never going to get back to 0. So, by the test for divergence, this series diverges. Right, so let me sort of go back through this last one real quick. So I had two different claims, right? So I had an that was eventually strictly positive. And the claim was if I took the limit of the ratio, if I got less than 1, it converged. If I got greater than 1, right, strictly less than 1, it converged. Strictly greater than 1, it diverges. So as a note, you should realize this also means that if it equals 1, this test fails, as opposed to succeeding in some positive sense, right, succeeding in that it converges, or succeeding in some negative sense, meaning that it diverges. Or I'm sort of arbitrarily using positive and negative, but it can succeed in either way, even though they have opposite outcomes. But it can also fail, because if the ratio is 1, I got nothing, right? So for my proof without loss of generality, I just assume it's always strictly positive, because I only care about the sort of eventually anyway. I don't care about first finitely many terms. For this convergent part, I basically picked a clever enough epsilon for the limit that I ended up getting exactly the situation with the first corollary, right? That this limit is uniformly bounded by an alpha after a big enough n value. And so since that alpha is less than 1, this thing converges, I'm all done. For the second one, I did something similar where I took a deep enough, right, a big enough value, n prime, so that if I took something bigger than that, the epsilon I chose guaranteed that I landed in an interval that was strictly larger than 1. Meaning that if the limit is larger than 1, strictly larger than 1, then I have that the top is strictly bigger than the bottom, meaning that I get something that is increasing, right? So I showed that this is an eventually increasing function, and since it is strictly positive somewhere, really, that as I go sort of far enough in, I will pass that point where it's positive and it's strictly increasing from there, so it can never come back to 0, which tells me that by the test for divergence, the infinite series diverges. Okay? So that is it. The one that you learned in Calc 2 is almost certainly the Cauchy's ratio test, which is sort of the culmination piece, the very nice version of this thing. But it doesn't sort of just come out of thin air. You have to do a little bit of work. It turns out you can do it, right? Like I could have, instead of citing these, proved these as subclaims. But historically, this is how it was done, right? You had the fundamental test, then the first corollary, and then eventually Cauchy's sort of nice last corollary. All right, so that is that. All of the ratio tests and their proofs.